Welcome to this video on chemistry required practicals for paper 2 of your GCSE exam. We'll cover everything you need to know for revision. This video is divided into 3 sections: practicals, techniques, and exam skills. We will cover the rate of reaction, chromatography, water purification, and much more. Required practicals are mandatory experiments set by AQA. Questions about them will appear in your written exams, so understanding them is crucial. These practicals matter for 3 main reasons. They form core exam content, test your method knowledge, and require strong data analysis skills. Always understand the why behind each step. Chapter 1 focuses on the rate of reaction, investigating the factors that affect how quickly a chemical reaction takes place. The rate of reaction measures how quickly reactants are converted into products. A faster rate means more product is made in less time. Remember the 3 types of variables: independent, dependent, and control. For a fair test, change only one independent variable, measure the dependent variable carefully, and control all others. Gas volume can be measured using a gas syringe or an inverted measuring cylinder over a trough of water. Record volume at timed intervals to plot a volume versus time graph. A rate of reaction graph shows a fast start, a steep rise, then slowing down, and finally levels off when one reactant is fully used up. The steeper the initial gradient, the faster the rate. Increasing temperature speeds up the reaction rate by giving particles more kinetic energy. This leads to more frequent and more energetic collisions that exceed the activation energy. The practical setup for temperature involves heating a water bath, mixing reactants and recording data, repeating for multiple temperatures, and then plotting the initial rate versus temperature. The classic sodium thiosulfate experiment measures reaction rate by timing how long a cloudy yellow precipitate takes to obscure a cross. Shorter time means a faster rate. Repeat this with different concentrations. Higher concentration means more particles and more frequent collisions, resulting in a faster rate. Rate is inversely proportional to time, so always calculate rate as 1 divided by time for exam questions. A catalyst lowers the activation energy of a reaction without being consumed itself. On a graph, a catalyst gives a steeper initial gradient, but levels off at the same final volume. Chapter 2 covers chromatography, which is used to separate and identify mixtures, typically using paper chromatography techniques. Paper chromatography separates mixtures of soluble substances based on how strongly each component is attracted to the stationary phase, which is the paper, versus the mobile phase, which is the solvent. To set up, draw a baseline in pencil, not pen, 1 centimeter from the bottom of the paper. Spot small dots of your samples onto this line. Lower the paper into the solvent, ensuring the baseline remains above the solvent level. Allow it to run and mark the solvent front immediately when removing the paper. To identify an unknown substance, run it alongside known reference substances. If 2 spots travel the same distance, they are likely the same substance. Remember, a pure substance produces only 1 spot, while a mixture produces multiple spots. The RF, or retention factor value, indicates how far a substance has traveled relative to the solvent front. Calculate it by dividing the distance traveled by the substance by the distance traveled by the solvent front. RF values are constant for a given substance in a given solvent. Chapter 3 covers water purification, focusing on techniques like filtration, crystallization, distillation, and methods for testing for purity. Water purification involves several separation techniques. For your exams, focus on filtration, crystallization, and the essential tests for purity. Filtration separates an insoluble solid, the residue, from a liquid, the filtrate. This uses a conical flask, a filter funnel, and filter paper, with a glass rod to safely guide the liquid. Crystallization separates a dissolved solid from a solution. The process involves heating the solution to concentrate the solute, cooling the filtrate to induce crystallization, and finally filtering and drying the pure crystals. Use filtration for an insoluble solid like sand in water. Use crystallization to recover a dissolved solid, such as copper sulfate, from a solution. When asked for pure crystals, mention both evaporation and cooling in your answer. Purity can be tested by checking melting and boiling points. A pure substance has sharp, fixed melting and boiling points. Impurities cause the substance to melt or boil over a range of temperatures. Chromatography also indicates purity, with a single spot meaning pure. Chapter 4 covers flame tests, a key method for identifying metal ions based on the characteristic color they produce when heated. Flame tests are crucial for identifying metal ions in a sample. When heated, these metal ions emit specific, distinct colors. revealing the identity of the metal present. The method involves 4 steps. First, clean the nichrome wire. Second, pick up the sample. Third, place the sample in the hottest part of the Bunsen flame. Fourth, record the flame color to identify the metal ion. Key flame colors include crimson red for lithium, persistent yellow for sodium, lilac for potassium, orange-red for calcium, and the most distinctive, blue-green for copper. Beyond flame tests, metal ions can be identified using sodium hydroxide solution. Adding NaOH produces colored precipitates, blue for copper, green for iron 2, brown or orange for iron 3, and white for calcium. Aluminum produces a white precipitate that dissolves in excess NaOH. Other nonmetal ions also have specific tests. Carbonate ions fizz when dilute acid is added, producing carbon dioxide that turns lime water milky. Sulfate ions produce a white precipitate when barium chloride solution is added after dilute HCl. Halide ions produce precipitates with silver nitrate, white for chloride, cream for bromide, and yellow for iodide. Chapter 5 is a recap of the essential gas tests. These methods are used to identify common gases produced during various chemical reactions. You must know the specific test and the distinctive positive result for several gases, as these are frequently tested in the exam. Hydrogen is confirmed by the squeaky pop when a lit splint is held at the mouth of the tube. Oxygen relights a glowing splint. Carbon dioxide turns lime water milky or cloudy. Chlorine bleaches damp litmus paper white. Learn these tests precisely. Chapter 6 covers exam preparation, including common question types, required math skills, and top tips for tackling paper 2. Recognizing common question patterns is vital for exam success. Examiners often repeat similar question types related to practical work every year. Expect questions asking you to describe a method, identify variables, interpret results by quoting data, and evaluate the method by suggesting improvements or sources of error. Key calculations include rate equations, RF values, mean values, and calculating the gradient of a graph for the instantaneous rate of reaction. When calculating the gradient, draw a tangent and use a large triangle for accuracy. For graph drawing, ensure you label both axes with quantity and unit. Use at least half the grid space for your points. Plot accurately with a small cross and draw a smooth line of best fit, ignoring anomalous points. For practical questions, be specific using chemistry terms, quote data to support your descriptions, state relevant safety precautions, and remember that repeating and taking a mean is a common improvement method. Understand the command words. Explain requires a reason using chemistry. Evaluate means weighing up evidence. State or identify simply require the answer without explanation. Match your response to the command word to score maximum marks. Avoid common mistakes, such as using a pen on the chromatography baseline or submerging the baseline in solvent. Always state multiple control variables and ensure the wire loop is clean before a flame test to prevent contamination. We have now reached the final chapter, summary and recap. This section brings together everything you need to know for your exam. Here's a quick glance at all 5 required practicals: rate of reaction, chromatography, water purification, flame tests, and gas tests. Review the core technique and objective for each. Finally, ensure you memorize the key formulas. Rate equals 1 over time, rate equals volume over time, RF value, and the gradient calculation for graphs. Good luck with your revision.